Hi everyone, my name is Yolanda, and today I'm going to talk about my final project, which is called Scene Graph-Based Instructional Task Helper, also known as SITE. This is also a project collaboration with Tsinghua University's Digital Manufacturing and Robotics team. So in recent years, large language models have shown remarkable promise in performing robotic tasks. However, they face a notable challenge. While LLMs excel in processing text, they struggle with visual data, which is essential for fully understanding an environment. Some research has tried to combine the strengths of vision models with LLMs. This approach typically encounters difficulties in matching visual input features with textual instructions. Alternatively, others have explored integrating vision and language models, VLMs, more seamlessly, aiming to more effectively unite these two elements. Nevertheless, images alone are insufficient to capture the complete context of a situation, and correlating pixel details with textual instructions is a complex task. The emerging solution is the use of scene graphs. These detailed semantic structures are being introduced in robotics to depict scenes more effectively than images alone. Although promising, incorporating scene graphs in task planning guided by natural language is still a relatively uncharted area in robotics research. So in my project, I utilize scene graph to enhance LM's understanding of the environment. This method overcomes the limitation of relying solely on visual data and improves the performance of tasks directed by natural language instructions. So now I will provide an overview of my method, SITE. Firstly, SITE is an innovative solution that transforms the way robots understand and interact with their environment. Unlike traditional methods that rely on images for environmental comprehension, SITE utilizes scene graphs. This approach provides a more structured and detailed representation of the surroundings, enabling a deeper understanding of the scene. So now let's delve into how SITE works. As you could see from the graphs on the right, the system combines scene graph, which describes the environment, with robot graphs that maintain the status of the robot. It uses graph attention networks along with large language models to integrate object features and relational understanding. This powerful combination allows SITE to match scene graphs with given instructions and accurately predict subtasks. These subtasks are essentially the specific, smaller tasks that robots need to execute, consisting of predefined actions and target objects within the scene graph. So moving on to the key contributions. The first contribution is the novel use of scene graph for robotic task planning. And second, our GAT-centric network, SITE, has been shown to surpass GPT-4 in task accuracy significantly. And third, we've also developed an innovative method for generating synthetic datasets tailored for graph-based robotic task planning. And this synthetic dataset are crucial for training our system to understand and execute tasks in a variety of scenarios. So now I would like to talk about some related work and where my work stands within these related work. In the field of robotics, the integration of language models has led to notable advancements. Robots are now better equipped to understand and execute complex tasks by interpreting language, thanks to improved vision and language processing technologies. First, we address the role of language models in robotics. Robots traditionally follow high-level instructions that are broken down into simpler subtasks. Our approach improved this by translating instructions into actionable items paired with objects, enhancing robot comprehension and effectiveness. This also allows for direct connections to robot APIs for expanded use. In motion planning, our method stands out by adopting an actionable format, which simplifies the transformation of verbal commands into robot actions. This approach is both efficient and flexible. With scene graphs, we have a robust framework for understanding the semantics of a scene. These graphs, when used with large language models, enable a more sophisticated task planning process. Our method effectively integrates scene graphs with instructions, improving task execution without extensive datasets. While scene graphs have been used for robot navigation and simple tasks, their application to complex instruction-based task planning has been limited. Our research leads the way by using graph networks and LMs to interpret scene graphs for advanced instruction processing. Large language models have significantly improved robotic systems' ability to understand complex instructions. However, combining this with visual information remains a challenge. Previous attempts required large data sets and often failed with new scenarios. And we use scene graphs instead of images, which allows us to utilize the rich semantic information they contain. And this enables robots to understand and navigate their environment without visual input, which is an advantage in changing or complex setting. And in summary, our innovative use of scene graph is significant in that we're enabling robots to not only receive instructions, but also understand the environment deeply, leading to a new level of autonomous task performance. Now I'll talk about size systems task definition, which uses computational frameworks to guide robotic actions. The system processes a combination of inputs. First, natural language instructions. Second, a scene graph, G sub S, and a robot graph, G sub R. These elements work together to predict the robot's next specific subtask. Our scene graph, G sub S equals set of N superscript S, E superscript S, and the robot graph, G sub R equals set of N superscript R, E superscript R, consists of nodes and edges. Nodes represent objects and their various attributes, while edges define the relationship among these objects. The subtask space is formally defined as P subspace equals A subspace cross O subspace. Here, A subspace represents a set of possible actions, while O subspace represents a set of object identifiers in the environment. This Cartesian product creates a framework for possible action object pairings for task prediction. So moving to equations, we have our predicted subtask, T equals set of A sub T, O sub T, where A sub T signifies the chosen action at time T, and O sub T indicates the target object. Post-action, the graphs are updated according to G sub R superscript T, refreshed to G sub R superscript T plus 1, and G sub S superscript T refreshed to G sub S superscript T plus 1, respectively. This update ensures that both the robot and environment are represented accurately for subsequent planning. So in practical terms, G sub R superscript T represents the robot's current status, including its location and item it's holding, in a graph format. The scene graph, G sub S superscript T, is built using advanced methods to accurately depict object positions and types. With an instruction input, site assesses the present state, predicts the immediate subtask, and then iteratively updates the graph states to facilitate the completion of the entire task sequence. So this process illustrates the dynamic capability of site, combining linguistic instructions with graph-based representations and predictive analytics to enable the robot to act with a high degree of autonomy. In this section, I'll provide an overview of the SITE methodology as illustrated in Figure 4. So SITE forecasts a pairing of action and object ID. Given an instruction I, a robot graph, R superscript T, and a scene graph, S superscript T at stage T. So the equation representing this process is equation 4. And for simplicity, we'll omit the stage label T in subsequent formulas. So SITE is a structured with an encoder-decoder architecture. The encoding process begins with a feature extractor that utilizes a shared weight, large language model, and 2 graph attention network modules. The input instruction, along with robot and scene graphs, are processed through the LLM, which serves as the textual foundation for semantic feature extraction. The 2 JT modules then extract structural features from each graph. Following this, a feature enhancer works to combine the instructional content with the graph formation. Finally, the task decoder synthesizes the enhanced feature to output the predicted action and object IDs. I will introduce these parts in detail in the next several slides. Moving forward in our exploration of the sight system, we reach the pivotal stage of feature enhancement. As illustrated in Figure 2, the feature enhancer employs a series of parallel multi-head cross-attention layers inspired by the methodology of grounding dyno. These cross-attention layers, labeled as CA, create a bridge for the flow of information between instruction features and graph features. We have two distinct cross-attention functions at play, CA sub I for instruction to graph and CA sub G for graph to instruction interactions. At each ICE layer, CA sub I operates with the word tokens from the instructions as queries and null tokens from the graphs as keys and values. This process enhances the instruction features with context from the graph data. Conversely, CA sub G takes the null tokens as queries and the instruction tokens as keys and values, enriching the graph features with linguistic details from the instruction. Post-enhancement, the instruction tokens evolve into fusion features, and graph tokens become graph queries. These are now ready for the task decoder, where the real-time decision-making process occurs, and the detailed math is explained in paper. So to summarize, the feature enhancer crucially synthesizes textual and graphical data, preparing them for the intricate task of decoding, which ultimately drives the robot's actions. We'll now examine the task decoder, a pivotal element within the sight framework, as showcased in Figure 3. The task decoder is tasked with converting the refined features into distinct subtasks, specifying the action and the target object. Diverging from traditional approaches that view subtasks as complete sentences, our model separates subtasks into two discrete elements. The separation facilitates a broader range of combinations between robotic atomic skills and objects in the environment, moving beyond the constraints of previous systems like Seiken or Lava. In our scene graph, objects are identified by unique IDs, avoiding the ambiguities associated with textual descriptions. These IDs ensure precision for the subsequent processing stages. The core of task decoder involves a transformer architecture divided into an encoder, ENC, ENC, and a decoder, DEC, DEC. Fusion features and graph queries are processed by these respective components, leading to the generation of output embeddings, both F superscript R and both F superscript S. And this is shown in equation 9. The action prediction involves mapping the robot graph's output embeddings to a action score using multi-layer perceptron, followed by a softmax function to pinpoint the most likely next action. This is shown in equation 10. For object prediction, output embeddings from the scene graph undergo scoring for each node through another MLP, determining the potential object for interaction. This is shown in equation 11. To summarize, the task decoder serves as the nexus where linguistic instructions and graph-based data are translated into robotic actions and object selections, guiding the robot with precision through its tasks. In this segment, we delve into the loss function, a critical component for training our sight systems model. Displayed in equation 11, the loss function is a key to refining the model's predictions for actions and objects. The loss function employs the standard categorical cross-entropy loss, denoted as L subscript act for the action branch and L subscript object for the object branch. These losses are calculated against the ground truth action ID and object ID, ensuring the model's outputs align with the correct targets. The total loss, L, combines these two losses and incorporates L1 and L2 regularization terms to prevent overfitting, and as shown in the equation. Here, alpha and beta represent the loss weights, while gamma and delta are the strengths of the L1 and L2 regularization, respectively. The WI, W sub I, denotes the trainable weights within the network. By fine-tuning these parameters, we guide the sight system to accurately predict the action to be taken and the object to be interacted with, ensuring robust performance even in complex scenarios. So now I'll introduce a sight data set This custom synthetic dataset is a comprehensive assembly of instructions, subtasks, robot graphs, and scene graphs designed specifically for robotic task planning. The graph construction of our dataset is methodical. Nodes representing environmental objects are linked by edges that describe their spatial relations, such as in, on, beside, and grasp. This framework is not just static, it's a dynamic graph representation that updates to mirror the interactions between the robot and objects, as well as the robot evolving state. Instructions and subtasks are structured intuitively. Human-generated commands guide the robot, with subtasks formatted in a straightforward action object ID syntax. For the data generation process, we simulate random domestic environments, which serve as the basis for initial scene graphs. A sequence of subtasks paired with instructions synthesized by ChatGPT-4 updates the graph step by step to reflect task progression. Finally, dataset statistics review the scope of our dataset. 5 datasets with object counts per scene ranging from 30 to 70. The largest dataset contains 20,000 instruction tasks broken down into 82,000 subtasks. We also included a dataset with unseen scenes to test and ensure the model's robustness. And here is the dataset statistics. Diving into the dataset statistics, our dataset categorizes subtasks based on actions, with each type having a unique action. Here's an overview. Table 2 shows the diversity of our dataset and our subtasks. For example, move object may involve moving an object to a specific location, while pick object involves grasping an object. This variety is key for training our model to handle a variety of actions. And Table 5 provides an example of instruction subtask pairs, offering a glimpse into the dataset's practical applications. For instance, please move the green dining table and place object there aligns with the subtask move place to finish, illustrating the task breakdown into actionable components for the robot. I will now talk about the experiments. I've conducted 3 experiments in total. So Table 1 represents an ablation study that highlights the importance of each model component by comparing the full site model against versions with key features removed. So the site without feature enhancer variant shows a decrease in task accuracy by nearly 8 percentage points, emphasizing the enhancer's role in performance. Even more critical are the JT models, as the site without JT model also sees a similar drop. Removing both features results in a drastic drop, demonstrating the essential natures of these components to the model's success. Additionally, Table 3 showcases site's ability to generalize to unseen scenes, maintaining high performance even in novel environments. This robustness is crucial for practical applications where model will encounter a variety of scenarios. And in Figure 5, we observe a performance comparison between site and GPT-4, showing site's superior accuracy across tasks with varying number of objects. These results highlight the model's adaptability and robustness, solidifying its potential for real-world applications. So as we look forward to the horizon of the site project, several exciting avenues of research lie in front of us. Firstly, we aim to enhance the site model's interaction with the environment by integrating real-time updating dynamic scene graphs. This will allow the model to respond to changes in the environment instantaneously, making it more adaptable and reflective of the physical world. Secondly, we're looking to broaden the versatility of the site model by adapting it for various robotic platforms. This adaptation will enable the model to support a wider range of robotic capabilities in physical forms, ensuring its applicability in diverse practical scenarios. And lastly, we plan to enrich our dataset to include a broader spectrum of complexities and diversities in the environment. By doing so, we'll train our model to handle an even greater array of tasks and challenges, pushing the boundaries of what robotic systems can achieve. And this is my final project presentation. Thank you very much.